and we need to solve something, a small oscillations of a rotating and translating hoop. And how can we do this? So let's read the statement of the problem that says an inextensible weightless thread is wound around a hoop, one end of which is directly attached to the sling, you can see, and the other through a weightless spring. Yeah, the mass of the hoop is a small m, that's right, and the spring constant is k. The hoop is slightly displaced downwards from its equilibrium position, and released. Oscillations will occur in which the hoop will move vertically and rotate at the same time. That's true. Find the frequency of these oscillations. So just wait. Before solving anything or before writing a thing, I would like to assume one thing. Let us denote the length of the spring in the undeformed state, the natural length of the spring, as L naught. And in equilibrium position, its length is, the length of the spring is L1. The length, total length of the spring is L1. So that I would like to write the condition of equilibrium in terms of forces. And you can see here two forces act, mg and the tension in the string, and so that the equilibrium condition can be written as mg equals 2t, and t here is k L1 minus L0. That's right, there is a change in the length of the spring, that is L1 minus L1 L0. And so I have the equation finally, mg equals 2k L1 minus L0. This is the one relation I have for future. And now I'm going to discuss the oscillation of this hoop. So start with this fact that the center of the hoop shifts downward from the equilibrium position, some equilibrium position, I don't know, but equilibrium position by a distance x. This is the equilibrium position and it has come down a distance x. Well, it will rotate, it is rotating as well, but I would like to write the potential energy of the system at this moment. And for a gravitational potential energy, the datum of the gravitational potential energy, where gravitational potential energy should be taken as 0, is the equilibrium position of the hoop, so that we can write the potential energy of the system simply by minus mgx, writing the potential energy of the hoop, and plus elastic potential energy. What is the change? Then the change in length of the spring, half k I would like to write, and it had some initial elastic potential energy stored in a spring was initially loaded by a length L1 minus L0. So a square of this, and now this is loaded by a length, its length has been increased by L1 minus L0 plus 2x. So a spring's final potential energy is this, and a spring initial potential energy is this. In the equilibrium position, the spring's potential energy is this, and right now its potential energy is this elastic potential energy, and this is the total change in potential energy of the system, because some elastic potential energy is stored in the spring now, and it has lost some gravitational potential energy, the hoop. And we are going to simplify this, so I can write minus mgx plus half k. I would like to take a common here, and so that I can write it L1 minus L0 square plus 4x square minus 2 into 2, that is 4 as well, that is 4x L1 minus L0 minus L1 minus L0 L1 minus L0 square, and that's get cancelled out, and 2 and 2, so that I can see I get something like minus mgx plus 2kx square, 2kx square plus 2kx square, and half was missing there, yeah, and oh no, that should be plus. Oh, I made several mistake, kindly check it out. And I guess I'm right now. I had made everything perhaps correct again, so this becomes 2kx L1 minus L0, and this is the change in potential energy of the system. And if I can use this equation, mg equals 2k L1 minus L0, oh, that means the whole result is simply 2kx square. Okay, this is the change in potential energy of the system. And what about the kinetic energy of the hoop? I don't care. It's rotational and translational kinetic energy is equal to, because it's also rolling here, because there is no slipping anywhere, so its rotational and translational kinetic energy will be same, and that will be its if it has been displaced by a distance b, so this its velocity of its center can be written as dx by dt, and it's still rolling, man, on the string. So its translational and kinetic energy will be same, so its total kinetic energy to its total kinetic energy will be mv square. B is dx by dt, half mv square plus half mv square. And if we equate them or write them, the total mechanical energy of the system as kinetic energy plus potential energy, and that is a constant, so I would like to differentiate it with respect to time like this. So that I could write here dE by dt equals 0, and this 0 will be equal to m 2b dB by dt plus 2k 2x dx by dt, and v is equal to dx by dt, and this 2 also get cancelled out. That means I get a relation something like dB by dt plus 2k by mx equal to 0, and you can see your omega equal to under root 2k by m, and that was all needed to find in this problem. Yeah, and I can solve it. Thank you very much for